Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we will simply continue our previous discussion on forced harmonic oscillator. As we said that instead of a pure harmonic oscillator, a forced harmonic oscillator's equation of dynamics is given by, we are just always talking the oscillator in one dimension, okay, for the sake of simplicity, and you know that once you know the solution in one dimension, for more than one dimension you can easily construct the solution. So, x double dot plus omega square x is equal to some f of t by m. So, this is a non-homogeneous second order. So, once again second order non-homogeneous linear ODE, ordinary differential equation in X. Okay. And we said that if f is periodic, so that means f by m some cos gamma t plus beta, then we can have some very interesting results, and we said that for example, in everyday life you can see the pushing of a swing in a park is exactly like a forced harmonic oscillation. Another point is that whenever we model crystalline solids, okay, their properties in solid state physics, in condensed matter physics, many a times the basic model comes from the knowledge of forced harmonic oscillator, that you can actually know whenever you follow in the solid state physics course of or a condensed matter physics course. Okay. Now, you will also see that this type of cases most often it is seen that finally the motion settles down with the same phase as that of the impingent force. Okay. That means, the phase part of the displacement is actually very similar to cos gamma t plus beta, and actually is equal to some constant times cos gamma t plus beta. And if you do, we said that you can show that the total solution, which is the combination of the complementary function, that is the solution of the homogeneous part and the particular integral, will be given by a cos omega t plus alpha plus f by m omega square minus gamma square cos gamma t plus beta. So, here you see that this is the natural frequency and this is the force frequency. This is the original initial phase of the system without any forcing, and this is the initial phase of the forcing term, okay, because the forcing is periodic, that is why it also has an initial possible initial phase which may or may not be 0. Okay. Now, whenever this type of equation is trustworthy, we can actually expect that this part is well behaved. That means, in other way, whenever omega is not equal to gamma, then we are saved. Then your x t is given by this solution, this thing. Okay. Now, what happens? What happens if omega is equal to gamma? Of course, you see this part will blow up, and for a finite value of x this has no value, no meaning, or you can simply say, okay, if it blows up and that we admit that x is blowing up, then again this is blowing up, this is blowing up, and this one is a forcing which we give from outside. So, we know that it must be finite, it can be controlled. So, something finite is equal to something infinite is not possible. So, there is a problem, and we concluded in the last lecture that so not a good solution for gamma is equal to omega. This case, this gamma is equal to omega case is actually known as the case of resonance. So, okay. So, resonance means when in the framework of a forced harmonic oscillator, resonance means that when the frequency of the periodic force acting on the system is exactly equal to the natural frequency of the system. Okay. But how to solve this situation? Can we have a better solution, and actually can we in fact try to understand that why this problem comes? So, actually as we will see at the end of this lecture, that this problem comes because of the assumption that the particular solution for x and the forcing term both have the same phase, the cosinus part. Okay. If one is cos and another is sin, is the problem solved? We do not know, that is exactly we are going to see, and for that what exactly will be very helpful for us is the complex analysis. That exactly is our next adventure. So, you see that we will now, instead of writing, so we now use complex notations. So, f t, which is nothing but f cos gamma t plus beta, can actually be written as real of a complex number f e to the power I gamma t plus beta, okay, where f is real and this part can be written as cos gamma t plus beta plus I sin gamma t plus beta, and if you take the real part you will simply have this part. Okay. I can do another thing, I can just write real, I can take f which is a constant and the constant part from here, which is e to the power I beta times the time dependent part e to the power I gamma t, and then I can call that is equal to R e f 0 e to the power I gamma t. This writing is actually a specific writing where you take all the constant part together and the time dependent part aside, and this is then another amplitude, it looks like another amplitude of this term, and without any time dependent part, but this is actually this part which is complex. So, this is a complex amplitude. Okay. So, we write here f to e to the I beta is the complex amplitude. You see that the initial phase part or the epoch part is actually absorbed in the complex amplitude part. So, if you write the complex amplitude notation, then there should not be any term with the beta or the initial phase separately. Now, what I can do with this? Okay, I can now write an equation complex which looks like d2y dt2 plus omega square y is equal to f0 e to the I gamma t by m, and if I write that and if I simply say okay, this is a complex, this is my claim of course that this is a complex form of the original equation which was d2x dt2 plus omega square x is equal to f0 by m cos gamma t plus beta. So, if I say that okay, if I take the real of this, that should give me this, then I can start from this equation and solve for y and finally take the real value of y to find the trustworthy solution for x. Okay, that I can do. So, what is the strategy? Once again, I design a differential equation with complex variable y in such a way that if you take the real part from both sides of the differential equation, then you will actually have the same equation as that of the real equation we tried to solve. Now, of course, one should understand at this point that here in this situation we are actually trying to solve this for the specific case gamma is equal to omega. So, at some point we also have to use that fact. Anyways, we start from this equation and we try to solve to find, our goal is to find y as a function of t and then to find real of y of t. Okay. So, that will somehow give us a solution which may solve the problem. Okay. Now, if you just so we try with trial solution. So, if you take y r proportional to just e to the I gamma t. Okay. So, that means that y r is equal to some, I do not know, some capital M e to the power I gamma t. Okay. Then of course, y r dot will simply be equal to, so I gamma m e to the I gamma t, and then y r double dot will simply be equal to, so another I gamma will come here. So, minus gamma square m e to the I gamma t. Okay. So, m e to the I gamma t is nothing but y r. I somehow mix some symbols. So, I write this as y r. I do not know why I wrote y r, but here since I am writing y r, I am just writing. Okay. So, I just change a little bit. So, the complex variable which I introduced is y r and not y. Okay. I mean, it does not make any difference anyways. So, y r, and that is why, so y r double dot is this. So, minus gamma square y r. So, you see that if this is the case, then the original equation gives, so this is minus gamma square y r plus omega square y r is equal to f 0 by m e to the I gamma t, and we are in a situation where gamma is equal to omega, that is why f 0 by m e to the I gamma t is equal to 0, and which is absurd, because it simply says that the forcing vanishes, and that is not possible. Okay. Because the forcing is the thing which is existing, and we are trying to find the distinction between a forced system to an unforced system. Okay. So, this is absurd. So, that means this trial solution will not work. If, I mean, from the theory of differential equations, you know, if in a linear equation, linear ODE, you have a failed solution of this type, then the next possible is, so then we assume a solution which is proportional to t times e to the I gamma t, and b should be the constant of proportionality. Okay. So, b is a constant. Then y r dot will simply be equal to b e to the I gamma t plus I gamma b t e to the I gamma t. So, it should be b times 1 plus I gamma t e to the power I gamma t. What is the double dot for y r? So, y r double dot will simply be equal to I b, yes. So, I have to just check this one, yes. So, it should be I b gamma 1 plus I gamma t e to the power I gamma t, because I first take the ddt over this term. So, one I gamma will come and this term will be unchanged. Then I will do ddt of this term, keeping this term unchanged, and that will give me I b gamma, right, plus I gamma b e to the I gamma t. Okay. And this will simply gives you this term will actually sum up with this term to finally give 2I b gamma e to the I gamma t minus, and this term now will be with a minus sign because I gives minus 1, gamma square bt e to the I gamma t. Okay. So, the final equation is, I again use a different color, final equation gives d2 yr dt2 plus omega square yr is equal to some what was the equation, I just check, f0 by m e to the I gamma t, f0 by m e to the I gamma t, and then you simply write that 2I b gamma minus gamma square b, I am just writing these two terms, and then plus this term I am writing omega square b e to the I gamma t is equal to, now I am writing f0 by m e to the I gamma t. I use the fact that we are considering resonance. So, this will go away, this will go away as gamma is equal to omega, and we have a very simplified formula 2IB gamma e to the I gamma t is equal to f0 by m e to the I gamma t. I can write everything now in terms of, so e to the I gamma t will go away and you have simply b will be equal to f0 by 2I m gamma, and since this is resonant condition, equivalently you can write f0 2I m omega. Okay. Now, you see what it changes in the solution. Okay. Now, y r is equal to f0 t by 2I omega m, okay, e to the power I omega t, and if you now take the real, so for our purpose, we need x which is real of y r, and which will now be, one can easily see, is equal to, so once again, so f0 you can again write, so f0 you should remember this is f0 small f0 e to the I beta, and if you write it completely you will see that this will be real of f t e to the I omega t plus beta by 2I omega m. Okay. At this point I would like to write that it much more carefully so that you understand what is happening. So, e to the I omega t plus beta is cos omega t plus beta plus I sin omega t plus beta. I am just writing this. So, real of f t cos omega t plus beta plus I sin omega t plus beta and then you write 2I omega m. Now you see, because you have an I over here, so this will go with this 1 over I, which is minus I, and this I will go away. So this will become actually the real part, and finally you will have this is equal to f t by 2 omega m sine omega t plus beta. What is the conclusion? So this is actually your x t. And so what is the conclusion? The conclusion is that when omega is equal to gamma, the particular integral part of the displacement is not in phase, but it is a 90-degree phase shifted with respect to the periodic force which is acting on the oscillator. Okay. But remember, here once again you should not be so happy that you just end here your business and you say, okay, I am done. The total solution is still not done. The total solution is then given by, so the total solution in resonance is given by, so I just write in resonance means gamma is equal to omega, is given by x is equal to a cos omega t plus alpha plus f by 2 m omega times t sine omega t plus beta. And here for every such expressions in resonance, you can invariably change omega and gamma. So all the omegas can also be written as gamma. So for example, you can also write a cos gamma t plus alpha plus f by 2 m gamma t sine gamma t plus beta. Okay, that is also equivalent. Okay. So now with this one, what is the good news? The good news is that here nothing is actually blowing up for finite t. Of course, you will see here one term is increasing linearly with t. So this is something which is increasing, but it is not blowing up for finite t. Okay. And that gives us actually a much more familiar picture and much more how to say like reasonable picture for a resonance. Okay. So if we now just draw this YR, so just this particular integral part, that the real part of this we can actually draw like this. So x particular integral. So I can, with respect to t, okay, you actually can have, so this part actually I am plotting. So you have this linear function xp is equal to f by 2 m omega t and xp is equal to minus f by 2 m omega t, and in between what you will have? You will have a pure sinusoidal movement with increasing amplitude. Okay. So that is the most conceivable picture of resonance in case of forced harmonic oscillator. Remember that the whole analysis was done neglecting any type of damping force or viscosity. Although in real system or real world you cannot have any system where viscosity is 0. So what will be the effect of viscosity in such a system? For that we first analyze a system with viscosity but without forcing, and then we will actually see in a system, in an oscillator, how this forcing and viscous effects they compete with each other one is trying to dissipate the energy and one is trying to pump the energy inside the system, and how they settle and whether actually or not they give a situation called resonance. Okay. With that, I am just wrapping up this lecture. Thank you.